Welcome, everyone. We are going to start off with chapter 13, and in this video, I'll be covering chapter 13.1, section 1 of chapter 13, which is about vector functions and space curves. In this chapter 13, you will be learning about what a vector function is and what are space curves and how do you represent them and some examples of space curves and the derivatives and integrals of vector functions, the length and curvature. And then also you're going to learn about motion in space. Um, and we are going to be explaining what velocity and how you compute the velocity and acceleration for a space curve. Okay, so now let's start with vector functions and space curves. What is a vector function? A vector function is a function whose domain is a set of real numbers and whose range is a set of vectors. So domain is a set of real numbers, and range is a set of vectors. For every real t in the domain of R, so note that it's a vector R, there is a unique vector V, vector in V, V3, denoted by R of t, vector R of t. If f of t, g of t, and h of t are components of the R vector R of t, then f, g, and h are real valued functions and they are called component functions of R. And we write R of t as f of t, comma, g of t, comma, h of t. This is in the angle bracket form. If you write that in ijk form, you know that you can write that as f of t I plus g of t j plus h of t k. And write like that. So just a quick recap of something about the parametric. T is a parameter. So earlier in your calculus 2 class, you saw about how we graph a parametric curve and what is the advantage of parametric curve versus Cartesian curve. So when you say circle, x square plus y square equal to, let's say, 4, then it's a circle of radius 2 with center at the origin. So that's all we can say. The orientation or the position of a particle at any instant is not known if you graph something in Cartesian form. But parametric form, if I write a function as x of t as say 2 cosine of t and y of t as 2 sine of t, then you know that x square plus y square would be 2 square cosine square plus 2 square sine square. So I can take the 4 out and this is equal to 4. And here t is said to be the parameter, and then the parameter can be from, it's a real number from 0 to 2 pi, or we can give a restriction for t. So in that case, the advantage is that when t equal to 0, you plug in t equal to 0 in both, then x equal to 2, y equal to 0. So it starts here and then at this position. And then when t equal to pi by 2, it goes to this position. So it is 2 r theta, r equal to, um, so it goes here. This is r theta. Then it goes here. The orientation, when theta equal to pi by 2, x equal to 0, y equal to 2, goes like this. And then it goes when theta equal to pi, it becomes x equal to negative 2, y becomes 0. So it also gives the orientation of the particle. It also tells that at a specific instant, at t equal to pi by 4, where the particle was at. So the advantage of parametric over Cartesian is that you're able to say not only the position, it also tells when the particle was at a specific instant, at a specific position. So all these are parametric curves are more gives more information about the motion of the particle. So when I say f of t, g of t, h of t, so each one, each component is a function of t. It depends on the variable parameter t. So vector function is, this is how we define a vector function. Limits and continuity. What do you mean by limits and continuity of a vector function? The limit of a vector function R is defined by taking the limits of the component functions. So when I say R of t, a vector function which is defined by the component form f of t, g of t, h of t, then limit as t approaching a of R of t. So I have to take the limit of each component. So it has to be limit as t approaching a of f of t, comma, limit as t approaching a of g of t, comma, limit as t approaching a of h of t. Okay. Then problem number 3, I would like you to refer to my video part of this section. This problem number 3 is done in the video section. Please refer to the videos. For this particular problem. Now let's define what space curves are. There is a close connection between continuous vector functions and space curves. Suppose that f, g, and h are continuous real-valued functions on an interval I, then the set C of all points x, y, z in space, where x equal to f of t, y equal to g of t, z equal to h of t, and t varies throughout the interval I, is called a space curve. The equations in 2 are called parametric equations of C, and T is called a parameter. We can think of C as being traced out by a moving particle whose position at time t is f of t, g of t, h of t. If we now consider the vector function r of t with the component forms ft, gt, h of t, then r of t is the position vector of the point P, is f of t, g of t, h of t as an ordered triple. So if you look at this picture, it will be, it will tell better. So for a parameter t, which is a real number, and this c, which is red, which is shown in pink, that is a space curve. Because it's parametric, it also shows the direction, where it starts, where it ends, how the orientation of the curve is. So, and then for any point P, you have the point, the position of the point is f of t, g of t, h of t at time t. And if you take the position vector, which is from the origin to that point, and it is r of t, which is defined by r of t, which you have to write in the component form because it's a vector. It has got magnitude and direction. You can also imagine a space curve to be the one that is traced out by the tip of this moving radius vector, that is the position vector r of t. So at different positions, different instants, the position of the particle will change. The position P, the point P will change. Then each time the tip of this moving vector traces out the space curve. Thus, any vector function R defines a space curve. So vector function can be thought of as a space curve See, that is traced out by the tip of the moving vector r of t, which is clear from the picture. So if you consider at a different time, then this will be the radius vector. If you consider a different time, this will be the radius vector and so on. So the tip of this moving vector traces out the space curve. So vector function, when you say vector function, you have to imagine that to be a space curve. What is the connection between vector functions and space curves? A continuous vector function R defines a space curve. That is traced out by the tip of the moving position vector R of t. Let's take this example. Sketch the curve whose vector equation is R of t equal to cosine t I plus sine t j plus t k. So when R of t is written in the ijk form, then you know that this, the first one, the chi component is x, and then the j component is y, then the k component is z. X of t and y of t, z of t, x is a function of t. So as you are given R of t equal to cosine t I plus sine t j plus t k, we know that x of t is cosine of t and y of t is sine of t and z of t is t. If you do x square plus y square, right, x of t square plus y of t square, you're going to square the cosine and the sine, which by Pythagorean identity equal to 1. Now what does this tell us? X square plus y square equal to 1 and z equal to t here. It can be any value. So x square plus y square equal to 1 in 3D is a cylinder because it has a missing variable. Is a cylinder whose base is a circle with radius 1 and center at the origin. So you have a space curve here. So let's give t, let's say t equal to, t equal to 0. Let's assume or substitute t equal to 0. So you get x of t equal to cosine of 0, which is equal to 1, and y of t equal to sine of 0, which is equal to 0, and z equal to t, which is equal to 0. So the point x, y, z becomes 1, 0, 0. So at t equal to 0, you have a point on the cylinder, which is this point 1, 0, 0. Same way at different values of t, substitute t equal to pi by 2. Then x of t would be cosine of pi by 2, which is equal to 0. And y of t is sine of pi by 2, which is equal to 1. And z of t is t, which is equal to pi by 2. So now what is that xyz? xyz point is x equal to 0, y equal to 1, z equal to pi by 2. So if you trace it, then you have to go 0 units along the x and 1 unit along the line parallel to the y-axis. And you have to move pi by 2 units upward, which will be this particular point. So it starts here, the curve starts here and goes in the anti-clockwise direction, right? It goes spirally counterclockwise. Okay. So you can check this for various values of t. T equal to pi, you can substitute. When t equal to pi, when t equal to pi, x would be cosine of pi. Cosine of pi is -1. Y equal to sine of pi, which is equal to 0, and z equal to pi. So it is -1, 0, pi. So it goes on the opposite side of x-axis, negative side of the x-axis. And then, so it's -1, and then from there you're climbing up pi units. So the spiral, so what it does is r of t, the space curve, the vector function, which is a space curve, is a spiral moving along counterclockwise on a cylinder whose radius is 1. So the center is on the z-axis. So the cylinder is made up of parallel lots of disks, and the disks are radius 1. So this is a cylinder whose equation is x square plus y square equal to 1. And what is shown in green is the space curve. The figure, it is a pink that is drawn counterclockwise. So you can see there's animation. This particular space curve is also named as helix. So this space curve is also named as helix. Called helix. You can also imagine it's something like an ant crawling on a Coca-Cola cylinder, a Coca-Cola can, or something like that. So on a cylinder, an ant is crawling. You can imagine like that. So let's see an animation for this. So you notice here, you have the spiral. Now you see this helix shown like a cylinder looking at only the space curve. And if you want to see where it is drawn on, so you see the cylinder as well, which is x square plus y square equal to 1. Sketch the curve, problem number 9. Sketch the curve with the given vector equation. Indicate with an arrow the direction in which t increases. Problem number 9. R of t as components t2 minus t, comma 2t. So this being the vector function, now the components are x of t, y of t, z of t. So if we write those, we get x of t equal to given as t, and y of t is the second component, and z of t is the third component. So earlier in 12.5, we saw that parametric representations of a line. So we can write this as 0 plus 1t. T can be written as 0 plus 1t. The idea is that we want to write this as x of t equal to x0 plus the direction, the x component of the direction vector times the parameter t. We want to write like that form to recognize what is the point through which the line is passing through and what is the direction vector of that line. So you know that line, in order to write down the parametric representation of a line, you need a point and you need the direction vector. So we want to recognize these parametric equation given here in the form of x0 plus at, y0 plus bt, and so on. That is 2 plus negative 1 times t, which is actually y0 plus bt. And z of t can be written as 0 plus 2t. So you can write that as z0 plus ct. So the above is, these are parametric forms of parametric representation of a line passing through the point x0, y0, z0, which is 0, 2, 0. So this is the point. x0, y0, z0 is the point. And A, B, C are the direction vectors. So A, B, C are the direction vector. So 0 to 0 is the point. And having direction vector, direction vector being vector, you write in the component form 1, negative 1, 2. 1, negative 1, 2. So we need to graph this. So we are, so the space curve here is after all a line, so that you have to know. And then it passes through this point and having a direction vector 1, negative 1, 2. We need to trace this. So the space curve is a line that passes through 0 to 0. Because you see only y coordinate 2, the rest of them are 0. It's a point on the y-axis. So it is 0 to 0. And then it has a direction vector 1, negative 1, 2. So the direction vector, so you have to make the line pass through this point in the direction of 1, negative 1, 2. Suppose you plot this point 1, negative 1, 2 in a separate graph. So you have to go 1 unit along the x direction and negative 1 unit along a line parallel to the negative y direction. So you're going to move along the line parallel to the negative y. So it is 1 here. Then you're moving towards the negative y direction, negative 1 unit, and then 2 units above along the line parallel to the z-axis. So your point is actually 1, negative 1, 2 is right here. So if you consider that as a vector, direction vector, and this O, if I call it some say Q, OQ, OQ is in this vector, OQ is the position vector, which has components 1, negative 1, 2. But our problem says that it's a line passing through this point in the direction of this OQ. So it has to be a line passing through 2, 0, 0 in the direction parallel to the one that is shown in this figure. So your line is like this, passing through 2, 0, 0 to 0 with the direction vector 1, negative 1, 2. So the space curve is a line in this case. As shown in this graph. Okay. So first you will be, in order to do the direction vector, you do the position vector of the direction vector, and then make sure your line passes through this point in the direction parallel to that position vector, OQ. Hope this video helps. And you have some more problems in this section done in my section videos. They will be problem number 18, Problem number 18 is done. So this problem you can see in the video section. Then problem number 27 is done as well. Then 31 and then 43 is there. And then in this exercise 31. So you have some more problems based on vector functions and how you can represent the vector function as a space curve. Some more examples. You can refer to my videos for this section. And I'll see you for my next video on 13 too.